Hello everyone, you're welcome to today's lesson. Today we are going to be talking about the long span of our panel 2. So we are done with the short span. We're going to continue from where we stopped. We're going to continue with the long span. So for the panel 2, recall that panel 2, the edge condition is one short edge discontinuous. And then we're going to obtain the moment coefficient for that particular panel. Now we'll call it panel 2, panel 2, panel 2, panel 2, edge condition, one short edge discontinuous. All right. Now we will obtain our moment coefficient. The moment coefficient, well, this is long span because we have done the short span. This is long span, right? So what is our moment coefficient? Positive moment coefficient is what? 0.028. Negative moment coefficient is what? 0.037. Okay. Now, then what was our UDL? Our UDL was, our UDL is 14.52 kilonewton per meter square. All right. Now, our new D. Remember that we are now designing for the long span of the same panel. So for our new D now becomes 124 minus 12, which is now equal to 112 millimeters. This is because the main reinforcement I've placed. The main reinforcement diameter is this. All right. Now the new effective depth is to remove the main reinforcement from the effective depth we had when we were solving for the shorter span. All right. This now becomes our new D. All right. We have gotten this. What are we supposed to get? The next one is to solve for our moment, to get our moment. All right. The positive moment is for the span, while the negative moment is for the support. That is the continuous edge. So first thing first, we have to work on the mid span. Mid span moment. M. Mid span moment M. Moment is equal to our positive 0.028 multiplied by 14.52 multiplied by 4.1125 square. This 4.1125 square is the shortest span of that panel 2. All right, that is why we're having it there. So if you compute this one will give me 6 points. My calculator, please. Get my calculator. If you compute this will give me 6 points. 6.88 kilonewton meter, which is the same thing as 6.88 exponential 6 Newton millimeters. All right, that is our moments. We have solved for the moments. Then we will now proceed to solving for our K. Our K is moment 6.88 exponential 6 over concrete cover, characteristic strength of concrete, which is 20, multiplied by 1000 multiplied by 112 square. This must be less than or equal to 0.156. So if you solve this one is less than 0.156, you use the lesser value. But if it is greater than, you use the lesser value. Okay? Now let's compute this. 6.88 exponential 6 divided by 20 multiplied by 1000 multiplied by 112 square. This one will give me 0.027, which is less than 0.156. You see, the difference is not much, but I just want to follow the right procedure. So we now calculate for LA. LA is equal to 0.5 plus square root of 0.25 minus K, 0.027 over 0.9. All right. So if you compute this must be less than what? Correct. This must be less than 0.95. Okay. So let's compute. If you compute and that is greater than 0.95, you use 0.95. But if 0.95 is greater than this, you use a lesser value. So let's compute. Square of 0.25 minus 0.0027 divide 0.9. So I give me, this is the same 0.5 plus 0.47. If you compute this, is equals to 0.97, which is greater than 0.95. So you use 0.95. Okay. Now the next step is Z. Calculate for Z. Z is equals to LA multiplied by D, which is equals to 0.95 multiplied by 112. Good. 112. This one will give you what? This one will give me 0.95 multiplied by 112. So I give me 106.4 millimeters. All right. What's the next step? Let us solve for our AS. AS required. Good. AS required is, what's our moment? 6.88 exponential 6 over what now? 0.95 multiplied by characteristic strength of steel multiplied by Z, 106.4. Okay? If you compute that, this one will give me 6.88 exponential 6 divided by 0.95 times 410 times 106.4. This one will give me 166.0 millimeter square approximately. Okay. Now the next step is to go to your BS code to get your nearest area. 12 mm. Yes, we are using 12 mm for the reinforcement. All right. Now, what is our area in the steel that is closer to 377? At what spacing? 300. So you now come to this point, you now provide wide 12 millimeter diameter bar at 300 mm center to center. This is now near bottom. Okay, we are providing 300 mm center to center, 12 mm reinforcement at 300 millimeter center to center near bottom. The reason why it is near bottom is we have already designed for, we have calculated for the knee span That's the shorter span. You understand? That now becomes the main reinforcement. That is the main bar. While this one is now the distribution. So this one is close to the bottom. So it's near bottom. Okay? We have gotten this. Our area provided, AS provided, be equal to 377 millimeter square. Okay? We have done that for the mid span of the long span. All right? Now we now go to continuous edge. Continuous edge. Continuous edge, there's a moment coefficient. What is that moment coefficient? Moment coefficient of that continuous edge, get it for me, is equal to 0.0 what? That moment coefficient, fast, the negative moment coefficient. Zero, is that the negative coefficient? Yes. 0.028. What was the the negative I'm talking? Good. 0.037. All right, this is the moment coefficient we're going to use for the continuous edge. Okay, so what we are supposed to do is to now get your moments. Remember, this is negative moment coefficient, this continuous edge. At the continuous edge, the tension is at the top. So that is why it's moment coefficient. The tension is at the top. All right, now this is not, we'll now calculate for the moment. This is, remember, this moment coefficient. Moment coefficient. We now calculate for the moment. Moment M is equals to 0.037 multiplied by our UDL 40.52 multiplied by short span 1125 square. All right. If you calculate this, if you compute this, you are going to have 0.037 multiplied by 14.52 multiplied by 4.1125 square. This one will give me 9.09 kilonewton per kilonewton meters, which is the same thing as 9.09 times 10 raised to the power 6 Newton millimeters. Okay, I think we can progress. We have gotten our moment. What's the next thing to calculate for? We have gotten our moment. The next thing to get is K. K is what now? 9.09 times 10 raised to the power 6 over, what is our characteristic strength of concrete? 20 multiplied by 1000 multiplied by our H, 12 square. This one will give me 9.09 exponential 6 divided by 20 times 1000 times 112 square. This will give me 0.036. All right. What is the next step? What are we looking for next? LA as the lever arm. We're going to get the lever arm now before we can now move time Z. Correct. So the lever arm. Lever arm is 0.5 plus square root of 0.25 minus our K, 0.036 over 0.9. Okay, this must be less than 0. Must be less than or equal to 0.95. All right, whichever is lesser, that's what we use. Okay, if this one is lesser, we use. If this one is lesser, we use this. Okay, let's compute again. Square root of 0.25 minus 0.036 divided by 0.9 equals to, this is equals to 0.5 plus 0.46, which is equals to 0.95. 6. This is also greater than 0.95. So use 0.95. Okay. So Z is what? Is equals to 0.95 multiplied by what? What's our L? The D 112, which is equal to 106.4 millimeters. Alright. What we have to calculate for now is what? AS required. Alright. This is equals to 9.09 multiplied 10 to the power 6 over what? 0.95. Alright. Multiplied by characteristic strength of steel 410 multiplied by what? 106.4. This is equal to, if you compute this, 9.09 exponential 6 divided by 0.95 410 multiplied by 106.4. This one will give me 219. Will give me 219.34 millimeters square. Okay, you now go to that table, the BS code. This one is close to 377, and again the standard of steel is so I don't want to use 300 in this case. I will use 250 in this case because our steel is not guaranteed. So the quality of the steel we produce is not guaranteed. So I'm going to provide what's the nearest one. I'll provide Y12 millimeter diameter bar at 250 millimeter center to center. This is what? Continuous edge is what? Where are we now placing this reinforcement? We are placing it at the top. Because I told you at the continuous edge, the tension is at the top. This is a hugging moment. Alright? This is a hugging moment. So the tension is at the top. So we are going to place this tension, this reinforcement at the top. Alright? So what is the AS provided? What is the AS provided in your table? At 250 center to center, what was it? What was it? 452 millimeters square. So we have, designed for the continuous edge. All right. So this is the step you have to follow in all the panels. You must repeat everything to make sure they meet specification. So they meet standards and that all the rules are followed. Okay. Now in this case, you are still going to check for deflection, but the same process we followed in panel 1, that's the same process we are going to use. Of course, the deflection will be satisfied. All right. So in our next class, we will now proceed to panel 3. That panel 3 is a simply supported slab. That is a one-way slab. All right. We are not using moment coefficient to calculating that. Panel 3 is a one-way slab. All right. We just apply the moment coefficient, the moment formula to calculate that. Then we still follow this step we are following now. So please, if you like the lecture, you want to be a civil engineer, you want to be good in design, follow my video, follow my classes. You get the formulas, then the method of how to analyze the structures from the beginning to the ending. Then if you have any question to ask, you can put it in the comment section, ask a question, then we'll talk one-on-one. Someone told me before that he has a question, so I'm waiting for your question so that we solve the question together. So all these things that I'm doing, we are still going to one, is how to detail your slab so that by the time the slab is subjected to loadings, the load will not impair the the appearance of the your slab. So that's what we are trying to do. We are calculating, we are getting the end product, which is the reinforcement. So the reinforcement is now what we're going to use, in constructing the slab. Okay, so that your slab will not be defective. There will be no failure. So if you have any question to ask, you can ask. Go to the comment section, you comment, you like, you share. Thank you, and God bless you. We meet again in our next class. In our next class, we'll be going straight to panel 3. So we'll solve all the panels, then we'll now go to beam straight. So because of the this class, panel, the designs, they are similar, but because of the class, we're not going to skip anything. So we'll analyze, we design all the panels, we'll go to all the beams, so that someone that is just coming will now follow. We now know how to design slab beam from one stage to the other, from step to step. Thank you, and God bless. Till we meet again in the next class.